So remember what we're talking about? We're talking about uniform convergence, right? Which I said is some sort of better version of convergence, right? You've got a bunch of functions, right? You've got a bunch of functions on some set, right? So you've got a bunch of functions. E is in some metric space, right? And right, so n equals 1 to infinity, right? And we say that right, that Fn converges uniformly to F means that what? What does Fn converging uniformly mean?
Epsilon 2.
What?
The epsilon 2.
That the epsilon 2, right? So given any epsilon, so here is F, right? And given any epsilon 2, right? So here is E, say, right? Given any epsilon 2 like this, then right, so given any epsilon, there exists an n such that if n is bigger than capital N, then the distance between Fnx and f of x is smaller than epsilon for all x in E. Right? And this is the key part, right? That for all x that that n works, right? That n works. Okay. And we said that that there's a Cauchy criterion, right? That this was equivalent to saying that for all epsilon greater than 0, there exists an n such that if n and m exceeded n, then fnx minus fmx was less than epsilon, again, for all x in E. Okay. Right. In other words, that you've got a Cauchy sequence, right? You've got a Cauchy sequence at each x, but it's not just Cauchy, it's uniformly Cauchy, right? This n works for all x. It's not that for each x you have an individual n that works. This n doesn't depend on x. Okay. Another way of rephrasing this. So is to say the following. Let m sub n be defined as the supremum of the difference between fnx and f of x over E. Okay. F sub n converges uniformly to f on E if and only if the limit of these m sub n's is 0 as n goes to infinity. Okay, right? Because for this limit to equal to 0 means that that you can make, given any epsilon, you can find an n past which this thing is smaller than that epsilon, right? You guys are still copying? Hold on for a second. Okay, so for this limit to be equal to 0 means that given any epsilon, you can find a capital N past which this is always less than epsilon, right? But that's saying that that for every x in E, this thing is less than epsilon, right? So this is exactly the same statement as uniform convergence. Okay. Okay. So so this is just to remind us what we're talking about. let me give a pretty important theorem called the Weierstrass M-test. So Weierstrass M-test. So again, we have a sequence of functions. We have a sequence of functions on some set E. Okay, so here it is. If each of the functions has a bound, and some m sub n, and this m sub n is not related to that m sub n, different m sub n. So each of the functions is bounded. Okay, right? For all x. So each f sub n has a bound. If the sum of the m sub n converges, suppose that the sum of the bounds converges, then summation f sub n converges uniformly. So, so the proof of this, you say, well, look, by the Cauchy criterion, it suffices to show that, you know, given any epsilon, there exists an n such that if m is bigger than n is bigger than capital N, then then the sum of f sub kx as k goes from n to m is less than epsilon for all x and e. That's what we need to show. Okay. I'll give you 1 minute to think about it. See if you can finish the proof. This is what we want to show. And we know that each of these guys is bounded and that the sum of the bounds converges. Say something, turn to your neighbor and say, I think we should use this. We should definitely use such and such a thing.
Comparison test.
What's the answer?
Comparison test.
Triangle inequality is right. So you say, well, look, right? We're trying to show that we can find an n such that this thing is smaller than epsilon. Right? You say, well, by triangle inequality, we know that this thing from k equals n to m is less than or equal to this thing from k equals n to m, right? Which is less than this thing from k equals n to m. Oops. So definitely the triangle inequality is involved, right? And so our question is then, do we know that we can find an n past which these guys are small? Right? And sure we do, right? Because this thing converges, right? Right? This thing converges, right? Since summation m sub n converges by Cauchy criterion, right? There definitely exists n such that if m and n are bigger than n, this thing is smaller than epsilon. Right? That's what the Cauchy criterion for series tells us. Right? This thing converges if and only if there exists some n. Given any epsilon, there exists some n such that the truncated tails past that point are all smaller than epsilon. Okay, so pretty simple theorem, but really useful. You'll see this used a lot. Oh yeah. If you take a course in complex analysis, you'll see this Weierstrass M-test all the time. Okay. Okay, so we had said that there was something good, there was something better about the uniform convergence, right? That if you're talking about pointwise convergence, then all these sort of unpleasant things happen, but with uniform convergence, things go better. So let's start talking about it. So uniform convergence and basic properties of calculus, basic concepts of calculus. Right. Supposedly, these things work together better than pointwise convergence. Okay. So we'll start off with the following, a little bit complicated theorem. So f sub n, which will tell us about the interaction of uniform convergence and continuity. Okay. So again, we have a sequence of functions. We have a sequence of functions, and on E, and we have some point. We have some limit point. We have some limit point of the domain. Okay. So if f sub n converges to f uniformly on E, then the limit of f of t as t goes to x equals the limit of f and t as t goes to x as n goes to infinity. So, right, this f of t, remember, is the limit of fnt as n goes to infinity. Right? So what this is saying is that we can change the order of limits, right? That you can take the limit of the sequence first, and then move the point, right? Let the point approach x, or you can first let the point approach x, and then take the limit as n goes to infinity. Okay. Now, this is not. You might think that this is f of x, but it's not, right? This is not f of x because x is not in E, right? X is not in E, so f is actually not defined on E, right? F is not defined on E, right? Not defined on x, not defined on x at x.
Wouldn't that imply E is open? Do we know that?
So f is not necessarily defined in X. Okay, so, right, the picture is sort of like this, right? That you have some set E, right? And you have this function f, right? And then you have these other guys, Fn, that are converging to f uniformly, right? And what this is saying is that you can, so here's your point x, which is a limit point here, right? X is a limit point, right? That you can take your function and let t go to x, right? Let t go to x, or you can let these guys go to x first, and then take their limit, and that'll be the same thing. Okay. So note that in particular, the limit, if we let a sub n be the limit of f sub n t as t goes to x, then the a sub n converge. The sequence converges. Right. Calling these guys a sub n. That limit is going to exist. Okay, okay. I think the thing to keep in mind is this picture here. Right? Here's this picture here. It says that, you know, if we go this way and then up, or we go up and then this way, you get the same thing. Okay, so let's do the proof of that. If it's not too hard. So our first thing is to let a sub n be defined as the limit of the fn's as t goes to x. And then we claim that, part one, we claim that the a sub n is a convergent sequence. So let's show that, suffices to show that the a sub n Cauchy is a Cauchy sequence. Okay. So, given an epsilon, right, we want to show that there's this n that works, you know, this n that works for this sequence, right? We have that these guys converge uniformly on E. Right? So, so let me. Okay. So. Uniform convergence implies that there exists an n such that n and m exceeding n implies that the functions differ by less than epsilon over 2 for all t. You want to think like this, right? That, look, we're trying to find an, oh, hold on. Yes, it's still ready. Okay, so remember what we're trying to do. We're trying to find an n such that past that n, the a sub n's are close to each other, right? Are within epsilon of each other. That's Cauchiness. Right? Okay. But remember, the a sub n's are the limits of the f sub n's. right? By uniform convergence, we know that we can make these guys within epsilon over 2 of each other. Well, then take the limit of them, and then the limits will be within epsilon of each other, right? We will be less than or equal to epsilon over 2 of each other, which is less than epsilon. Okay, and that's it, right? So, right. So let t go to x, and we end up with a sub n minus a sub n is less than or equal to epsilon over 2. Well, that's good enough. Yeah, Ari.
So you're taking that limit of
This thing
Yeah.
here, yeah. Right, we have this inequality, and let t go to x in that inequality, we get the limits. Okay. So we're done, right? The a sub n's are cushy, and so they converge. Okay, so now part 2, so this is part 1. Part 2, we want to show that the limit of f sub t as t approaches x is that limit of the a sub n's, right, as n goes to infinity. Okay, which we'll call this thing A. Okay, so what do we want? We want to show that right, that this limit is A. Right. So we want to show that given any epsilon, right, for all epsilon greater than 0, there exists a neighborhood V of x, right, such that f of t minus A is less than epsilon for all t in V intersect B. Excluding x. Okay, so so the proof is simple. We just use the triangle inequality. So we say, okay, by triangle inequality, the distance between f of t and A, well, that's less than or equal to the distance between f of t minus fnt plus fnt minus a sub n plus a sub n minus a. Why did we split things up like this? The reason we split things up like this is because we have 3 facts, right? We have 3 facts. What do we have? That the f sub n converge to f uniformly, right? We have only 3 facts. 1, f sub n converge to f uniformly, right? 2, the a sub n converge to a, and 3, that the limit of f sub n t is a sub n as n goes to infinity, or as t goes to x. Right. So since we have those 3 facts, those are the ones we're going to use. So we rewrite this in terms of things that over which we have control. Okay. So since fn converges to f uniformly, and a sub n goes to a, we know that there exists an n such that f of t minus f of t is smaller than epsilon over 3 for all t in E. Right? So this is true for all t in E, right?
Where did epsilon over 3 come from?
We're trying to show that given an epsilon that we can make this thing smaller than epsilon, right? We've divided this thing into 3 parts. We're going to make each one smaller than epsilon over 3. Right? That's sort of the usual thing. Right? We'll show that this is smaller than epsilon over 3, this one is smaller than epsilon over 3, this one is smaller than epsilon over 3, so the sum is smaller than epsilon. And this is the usual ridicule of analysis. Okay. It all boils down to 1/2 plus 1/2 equaling 1, or something along those lines. Okay. So there exists an n such that this happens, and also such that this happens, right?
Are we saying there's an n such that an n past that?
No, actually.
Interesting.
Yeah. We don't need to. We just need some n. We just need some n for which that happens. Yeah. Okay. Further, since the limit of fmt is a sub n, as as t goes to x, right? We know that there exists a neighborhood v of x such that fnt minus a sub n is smaller than epsilon over 3, right? In that neighborhood for all t in v intersect e excluding x. Yeah, Mo.
Why can we say that the n for 1 and 2 over there is the same n? Is that us calling on there exists an n past which in the earlier definitions?
Yes. Yes. So I guess probably the procedure would be to do this part first. You would say, well, look, I know that there's a big N past which all these guys are less than epsilon over 3, right? And so I choose this little n to exceed that big N, right? So this is going to hold true. Now, no. Actually, just you hold that big N. You hold that big N in your mind, basically. You say, I know that for all little n big past that, this is going to be true, right? Further, I know that there's another big N past which all n, past which this thing is true, right? And then you would say, take the max of those two and choose one guy that exceeds both of those guys. But you only need to choose one, which is you only need to choose one thing. Okay. So you've chosen that one guy, right? So you've chosen, here's your tube, right? And you've chosen that one guy that lies in the epsilon over 3 tube, right? So you've chosen your one guy so that it lies in the epsilon over 3 tube, and also a sub n is in the epsilon over 3 tube. Okay, but since the limit of this thing, since the limit of this thing is a sub n, well, you know that there's some neighborhood, right? If this is x, there's some neighborhood of x in which fnt is close to a sub n. right? Because the limit is a sub n, right? So that means that some neighborhood of x, in some neighborhood of x, these guys are within epsilon over 3 of a sub n. Okay, right? So then you're done, right? You've got it all together, right? So in that neighborhood, all of these three things happen, and so this thing is going to be less than epsilon. Right? So thus, in this V intersect E excluding x, we know that f of t minus a is less than or equal to epsilon over 3 plus epsilon over 3 plus epsilon over 3, which equals epsilon. I guess I should have made one of these guys smaller because I have less than or equal to, but it doesn't matter, of course. Okay. Okay. So let me write up the statement again. Right. This says that so here what we've just shown is that if Fn converges to F uniformly on E, then the limit of f of t as t goes to x equals the limit of fn of t as t goes to x, and then as n goes to infinity. So here's a corollary. Suppose that so if the Fn are continuous, suppose the Fn are continuous. Okay. So now we're talking about x. Now x is actually part of E. Okay. Now x is actually part of E. Right, because we want to talk about continuity at x. Okay, what if x is part of what if x is part of E and the f sub n are continuous? Well, if the f sub n are continuous, then what's the limit of fn t as t goes to x? It's going to be f of x, fn x, right? Right, because that's what continuity means, that the limit actually takes on the value at x. Okay, so if the fn are continuous, we would get that the limit as n goes to infinity of the fn x equals the limit of f of t as t goes to x, right? But what's this? The limit of fn x as n goes to infinity. It's f, right? The fn converge to f on E. And so this would be f of x would be the limit of f of t as t goes to x. So if these guys are continuous, we get, right? And what does that say? That says that f is continuous, right? i.e. f is continuous at x. Okay, so that gives us the corollary, right? That if you have a sequence of functions, and if the fn are continuous and the fn converge to some function f, then that f is continuous also. then that f is continuous also. Okay. That is the uniform, if these guys are all continuous and converge uniformly to something, then that thing is going to be continuous also. Okay. So taking the limit preserves continuity if we're talking about uniform convergence. Yes, Susan?
Does the double arrow mean convergence or just
Uniform convergence.
Okay.
Uniform convergence. Right. So say it again. Right. If you've got continuous functions and they converge uniformly, then the limit is also going to be continuous. Now that's not true for pointwise convergence. Remember, right? We had last time we looked at this function, right? F of x is x to the n. These guys are all continuous, but the pointwise limit was discontinuous, right? Each of these guys was continuous. The pointwise limit was discontinuous, right? But that can't happen if you've got if your sequence is uniformly convergent. Okay. That's a pretty important result. So uniform convergence is better. Brian, do you have a question? Can I? No. Everybody all right? Okay. So, so the theorem that you would like to have is that pointwise convergence on a compact set implies uniform convergence. That would be cool, right? If you had like pointwise convergence on a compact set, then that somehow guarantees uniform convergence. It's not true. Why is it not true? Here's your example. Right? Pointwise convergence, the set is compact, but the convergence is not uniform. Convergence is not uniform. Okay, but you do have, there is sort of a weak theorem that we do have. That's kind of cool. So say that Fn converges to F pointwise on a set on a set K. If the Fn and F are all continuous, if the Fn are decreasing, right? So they're shrinking at each point. You get a decreasing sequence. And K is compact, then then the convergence is uniform. Okay, so let's do the proof of this. Proof of this is kind of cool. You say, okay, well, we want to show uniform convergence, right? We want to show that given any epsilon, there exists an n such that the distance between f and x and f of x is smaller than epsilon for all x and k. Right. So you've got this decreasing, right? Here's Fn, Fn plus 1, Fn plus 2, and so on and so forth. And they decrease down to some function f. Okay. And we're trying to show that there's some n such that if n exceeds n, then this is true for all x and k. Okay, but notice that it suffices to show that for some n, this is true, right? That fn x minus f of x is less than epsilon for all x and k. Right? Because since the fn plus 1 is less than or equal to fn for all x, right? Your sequence, your functions are getting lower, right? Your functions are getting lower, and so this thing is always going to be positive, right? Fn x minus f of x is always going to be positive, so I can get rid of the absolute value signs, right? 2, if it happens that at some n this is true, it's certainly going to happen for all n past that, right? Because everybody else is lower, right? So all I have to do is show at some point this happens, right? At some point this happens, and then because of the decreasing stuff, it's going to happen forever after. Okay. So we do something clever. We say we rephrase the problem. Rephrase the problem. Let k sub n be all points in K such that f sub n x minus f of x is greater than or equal to epsilon. Okay, so that is, we look at here's our f, and here suppose is our f. Here suppose is our f sub n, right? And here's our epsilon 2, right? We're trying to show that at some point this guy gets inside the epsilon 2, right? As n goes big, this guy eventually gets inside the epsilon 2. So we create this set k sub n, which says, tell me the bad parts, right? So I say, well, look, right? These from here to here were bad, right? From here to here, we're bad, right? From here to here, we're also bad. From here onwards, we're bad, right? Tell me the bad points, right? Tell me the bad points for the nth function. Okay, I'm hoping that the set of bad points eventually becomes empty, right? If it's empty, that means that you're inside the tube. Okay, so that's our hope, right? Our hope is that k sub n eventually is empty. Right? K sub n is empty at some point. Right? That's what we're hoping for. That k sub n is eventually empty. Now observe when k sub n if we look at k sub n plus 1, it's included inside k sub n, right? Because your functions are decreasing, right? Your functions are decreasing, so the bad points of the next guy, are smaller than the bad points of this guy, are included in the bad points of this guy, right? You're not going to have the case where you get some new bad points, right? Because that would mean that your function had gone over the previous guy. That's not possible. Okay, so the k sub n are nested. K sub n are nested, right? K sub n are nested. Two, the k sub n are, what am I going to say? We have only 1 minute. This k sub n are compact. K sub n are compact. Why are they compact? Well, they're subsets of a compact set, right?
They closed.
And they're closed, right? They're closed, are closed, and they're subsets of K, right? Why are they closed? Because they're the preimage of a closed set, right? If you define G sub n as f sub n minus f, okay. This is a continuous function, right? This is a continuous function. It's a difference of continuous function. And you're taking the preimage of E infinity, right? This K is actually G sub n preimage of E comma infinity, which is a closed set, right? So you're taking the preimage of a closed set through a continuous function, so it's closed. Okay. Last, if we intersect all the case events, case events, we get the empty set, right? Because to be in all the case events would mean that that this thing is bigger than epsilon for every n, right? But the f's and k's converge to f at every point, right? So at every point, right, this is going to go to this goes to 0, right? So the intersection is the empty set, right? There's no point that fails for every n. Okay, so this is empty. Okay, so here we've got a nested set of compact sets, a nested collection of compact sets, and their intersection is empty. What does that tell us? Max?
At least one of the sets is empty.
At least one of the sets must be empty, right? Right? Because otherwise, right, if these guys satisfy the finite intersection property, right, then you know that there's going to be that the intersection will be non-empty, right? So you must fail the finite intersection property, right? And so there must be one that's non-empty, that is empty. Right? So thus, the case of n must fail the finite intersection property. Right? So there's a case of n that's empty. But that's what we wanted, right? We wanted to show that one of the case events was empty. Remember, the finite intersection property said that if any finite collection of them has a non-empty intersection, then then the total intersection would be non-empty also, right? So it must be that you fail the finite intersection property. So one of these guys is empty. Okay, sorry to keep you over. That's it for today.